Okay, but I hope you're excited about this unit. So the last 4 weeks are regression. So we're going to do just a basic one variable regression. Next week, we'll do multiple variables, how to do like a larger regression with multiple independent variables. Then lesson 13 is not anything new. There's no instruction in lesson 13. It's simply like you do a kind of more in-depth challenge assignment where you're trying to put together a good regression model, use that model to make predictions and make a business decision to maximize profit. So we're trying to see how this might work. It's a hypothetical example. The regression model is way too good. You will never find a regression model in real life with like a 99% R squared, which you'll learn what that is. You probably learned what that is this week. But on the challenge on lesson 13, you'll learn that. We will be in this case where the R squared is insanely high and you can make really precise predictions just to give you, a false sense of skill or something. And then lesson 14 will be logistic regression when you have a binary dependent variable, and we'll be predicting Titanic survival, which is kind of fun. Well, it's fun now that it's been like over 100 years since it sank. It was probably pretty depressing in the immediate aftermath. Okay, so this is like skills that I think are really widely applicable. Any field, no matter what, regression is going to be used. So we're going to do, and something different about this recitation session this week is instead of using a different data set and then doing some of the same things to see it modeled, I'm using this same data set for the recitation session as you're using on your assignment. And the reason is this is like such a historically important data set. So when I took statistics as an undergrad, I was a statistics major and I took my very first statistics class. And we used this really non-traditional textbook that gave like the history of some of these statistical tests. And it showed us the history of the regression line developed by, I forget who, I think Pearson might have been, it was before Pearson's time, is like the famous statistician. But this father-son data set was sort of where the name regression came from. And so it was really cool. I really enjoyed learning it that way. And so I wanted to share some of that joy with you. So we're going to start this father-son data set, right? So we measured a bunch of fathers, we measured their height, we measured the heights of their sons. So we have this data set that just has the two variables, father's height, son's height. That's it. And we think one will be predictive of the other. So we're just going to do this quick scatter plot first. Okay, so we're gonna, whoa, dang it. Shoot. I don't even know what button that was. I wish I knew because I want to get rid of this. Let's go view. I accidentally hit some kind of Control-Shift combination. I did that. I wish I knew how to do that so I knew how to undo it faster. All right. Okay. ggplot first, our data is going to be fs. And then our anesthetic statement, x equals what and y equals what. Let's take a look at the data really quickly. So we just have father, son, right? All we have is their heights measured in inches. Okay, x equals what? I think I've mentioned this briefly, but now that we're in regression, we need to formalize this. We have the y variable, we have the x variable. The y variable is what? The one, it's going to be son's height in this case. And why is that? Why do we want son's height on the y-axis and father's heights on the x-axis?
Dependent on the y.
Yeah, dependent on the y, right? Dependent variable is the one you're predicting. So we're saying father's height predicts son's height. And that implies a direction of causality. If you have a tall father, that causes your son to be taller on average, not the other way around, right? Like, because temporal precedence, right? Like, father came first, right? So it's probably the father passing his height onto the son and not vice versa, right? So that's why we're going to say x equals father, because that explains some aspect of the son's height. So we put that on the y-axis, and we're going to just do a simple scatter plot, which is geom point. But then it also says use the classic theme. So I'll add theme underscore classic. Okay, so we have this plot. You can clearly see a relationship. It's not as strong as you might expect, but there is a strong relation. There's a relationship. Depending on your on your expectations. The reason I think this data set is so critical is because like the means are pretty comparable. Yeah, there's a lot of important things, and we're actually going to illustrate those things now, like why historically this became so important for the development of the regression line. Okay, so we want for both fathers and the sons, we want to calculate mean, standard deviation, minimum, maximum. Okay, I'll go ahead and use dplyr for this. We'll just do it all in one system of commands. So we're going to start with fs. And so to do that calculation, what do? What's the verb, the dplyr verb we use?
Summarize.
Yeah, just summarize. And we don't have to group by anything because they're just, yeah, we're not grouping by father or son because those are just two different variables, right? So we want, and we'll call this mean son is going to be mean of son. Say mean father is going to be mean of father. That is the name, right? Father and son. When we had it, father and son. Yeah, those are the names of the variables there. Okay, we'll say SD son is going to be SD of son. Then we want also the maximum. So max son is max of son. Max father is max of father. Min son is min. Oops. I hate having to type down like this. That's why all these little typos. And then min of father. Min of father. And I can bring that up here. Either way. Okay. Okay, so here's the critical thing, and this is like the historical context. We say, okay, are the sons shorter than the fathers? No, on average, they're an inch taller, right? So it's not the case that sons tend to be shorter than fathers. So the averages are pretty comparable, almost exactly an inch higher for the sons, maybe some improved protein. This is back in the 1920s or something. So improved protein provision for sons made them on average just a little bit taller. Are the sons' heights less variant than fathers' heights? Right? Do the sons' heights get, more squished? No, the son SD of the son is a little bit higher than SD of the father, probably not meaningfully larger. So basically the same variance. It's not that sons' heights are getting more squished down towards the mean. Okay, and that's a really important sort of historical thing we'll discuss a little bit later. All right, now it says redo the same scatter plot, but this time we're going to add this line. So there's this geom AB line, and we're going to add this red line, and then we're going to just take a look at it. So, okay, so we're going to copy this code. Okay, and then we can add, which is the great thing about ggplot, is we can literally just add it, plus, and then we'll just copy this line of code. So this geom AB line, and to give you a little bit of context for how this code works, geom AB line is add a line to this plot, and I tell you I want the slope to be 1.025627, and I want the intercept to be negative 0.737. So with an intercept and slope, we can draw a line, and then I just made it red. Okay, so if we take a look at this line, that line kind of seems to fit, right? It kind of, and that slope of that line is the standard deviation of y over the standard deviation of x. The standard deviation of x and y are basically the same, right? That's how much variance there is in the sons and fathers' heights. So they're basically the same. So it's a slope of 1, okay? And I tell you right here in the instruction, the line this isn't the regression line, but it kind of looks like it fits, right? It could be the regression line, but it's actually not the regression line. Okay, if this were the regression line, what would be the interpretation of that slope, which is basically 1? What's the interpretation of the slope? Every time we do a slope on any line, including the regression line, it's basically a 1 unit increase in x equals a slope unit increase in y, right? Since our slope is 1, it's a 1-to-1 correspondence. Basically, every inch that the father grows, we expect their son to also be 1 inch taller, right? So if you have a man who's 6 feet tall, we expect their son to be about 6 feet tall because like their heights basically match up here. If that father is actually 6'1", we expect their son to be 6'1". If that father is 6'2", we expect the son to be 6'2". Every inch the father grows, we expect the son to be an inch taller. That is, if this were the regression line. It turns out it's not the regression line. But it's like not a bad first guess, right? The standard deviation of y, how y varies relative to how much x varies. You draw a line, it goes straight through that cloud of points, right? Seems like a good regression line. And here's why it's not a good regression line. And if you look at it a little more carefully, you can see why that makes a bad regression line. And that is, you say, hey, what's my guess? Here's somebody who's 72 inches tall, right here where my cursor is. So 72 inches tall. Our guess is that their son is going to be 73 inches tall, right? That's basically the sons are an inch taller, right? If that were our guess, if this were our regression line, I'm guessing a 6'2" father has a 6'3" inch son. But in reality, the people who are around 6'2", take a look here. We have like these maybe 10 people who are actually taller than 6'3". But then we have like these 30 people who are below 6'3". Right, so that's a bad guess. If we're like, we take a tall father and we guess their son's going to be about the same height, maybe an inch taller, like the mean is shifted up. That's a really bad guess. We're over predicting their height, right? Whereas if we go in the opposite direction, let's take a look at people who are 62 inches tall. So they're 5'2", pretty short on average man. And you say, okay, we're going to think you're a short man. Your son's also going to be short. Do we think your son's going to be maybe 6'1"? Or sorry, 5'1", no, 5'3", right? 5'2", 62 inches. We're going to predict 63 inches, right? If we make that prediction, that's about where this is. That's 63 inches. If that's our prediction for a 62-inch tall father, we underpredict almost all of them, right? All of these are here versus the over predictions are very slight, right? And so even though this line seems like it's going through the points pretty well, it makes really bad predictions on the end. Okay, so it seems like it fits, but it turns out we're making really bad predictions. Okay, this is where regression comes in. Okay, so if you use a father's height to guess the son's height with that red line, you're going to be systematically too tall for the tall fathers, too short for the short fathers. And that's where regression comes in. The word regress means to pull towards the middle. Right, so the actual regression line is less steep. We actually say, oh, if you're 6'3", your son's going to be about 6 feet, not 6'3". If you're 5'2", your son's not going to be 5'2". He's going to be more like 5'5", 5'6". Right, we have this regression. The line comes closer to the average. Okay, and so here is the actual slope for the regression line. We take, remember the line I just showed you was the standard deviation of y divided by the standard deviation of x. The formula for the slope is you take that number we just got and you multiply it by the correlation. Okay, so we're going to manually calculate the correlation by taking the correlation. How do we calculate correlation? Have we done it before? It's just core. Okay, so we know the correlation of the fathers and sons' heights. So we just put in FS $ father and FS $ son. I'm just going to execute that so we see. Okay, the correlation is 0.501. So we have this correlation, and then we're going to multiply that by standard deviation of father's heights we have up here. SD father is 2.745827. We multiply that by here, and then divide by the standard deviation of, I got it backwards. I always get this backwards. Which is y, father or son? Y, yeah, y is son. So I did that wrong. We want to multiply by the father's standard deviation. So that's 2, which is what we just got. No, so we want to multiply by sons because that's y, right? SD of y means the standard deviation of the son's height. So multiply by the son's heights, the son standard deviation, divided by the father's standard deviation. I very frequently, for some reason on this data set, I always mix up y and x. So y is the son's, x is the father's. So this is the standard deviation of the son's heights. This is the standard deviation of the father's heights. Okay, but then we multiply it by this correlation of 0.5. So the actual regression line, slope is 0.514, not 1. Okay, somebody tell me in their own words, what is our interpretation? Or you can use my words, just replace it, right? What's the interpretation of this slope? I want to have you to do this. When I pretended before that the slope was 1, I told you what it was, right? But now it's 0.5. So you can use my same words if you remember the gist. Yeah.
Isn't it like each unit, like
Increase in
Increase
x,
in-
which is what? What is it? What are the units in x? The height of the father. So for every inch, a father gets taller.
then the sun gets taller by 0.51 the slope?
Yeah. So for every inch a father is taller, we expect their son to be a ½ inch taller. Not a full inch taller, just a ½ inch taller. Okay. All right, and now we're going to do a little bit of math. So the slope of the regression line is 0.514. We just calculated, right? So what's the y-intercept? Okay, I'm going to highlight this so you can see this. Okay, here is our formula for a line, right? Y equals, remember back in algebra, probably 7th or 8th grade, y equals mx plus b, right? The m is the slope, b is the intercept. We do the same thing, only we just call it b0 and b1. Or if you want to be fancy, you call it beta 0 and beta 1, the Greek letters, right? So we just switch the order. Nothing different. B1 is our slope, which we know is 0.514. B naught is the one thing we need to know, right? We have 4 unknowns. Now one of them's known. We know the slope. If we want to get B naught, what do we need? We need y and x. Okay, what do we know about regression lines? The one thing you should know is that in a single regression line, it will always go through the mean of x and y. So this line, if you go for the mean, this line, the regression line and this line is always going to go through the mean. Okay, so we know an x and y point. We know a y point of 68 point. I'm going to write it here. So we know y, I'm going to put in the average. So y is 68.68423 equals B0, okay, B0 plus B1 times x, only we know B1 is 0.514, was it? What was the slope?
0.514.
0.514, and then we know that x is the father's heights, right? We're going to put in the mean. So we know an x and y point on the line will be the mean of x and y. So we're going to put 67.6863. We're solving for this. Okay. Maybe it's been a while since you've done basic algebra. So this might not come immediately to mind, but it should be, you should be able to do this, right? Basic algebra should not be beyond your skill set. Even if you're rusty, that doesn't mean rusty is not the same thing as being unable. Right? So solve for that. We have, how do we get rid of this? We want B naught by itself. What do? We just subtract this from both sides, right? So to find the intercept, all we need to do is we go, okay, let's start with our multiplication on that side. So 0.5140059. Remember, I've told you can do basic math in R. So let's do the basic math here. Times 67.6863 is 34.79, and we want to subtract that. So we're going to subtract that from 68.68423. Okay, and R is good with order of operations, so we don't actually have to put a parentheses around this because R knows order of operations math or multiplication comes before subtraction or addition. But if you want to just make yourself feel better, you can put the parentheses around that. So our intercept is 33.89307, and our slope is 0.514. Okay, now it says, draw this GeoMAB line again on this plot. So we're going to take the same plot, but I'm going to add the real regression line now. That red line was not the real regression line, but we can do another AB line. So we say geom_AB line, and there's two things we have to put in there, the slope and the intercept. The slope is 0.5140059. That might be a little overkill on the decimals. We probably don't need that many decimals, but precision usually doesn't hurt unless it's in a final report. Being overly precise with that many decimals in a final report to somebody's probably makes you look kind of silly. But when it comes to doing calculations, being over precise is not a bad thing. Okay, so we're gonna have two lines. Our real regression line, that red fake sort of red herring line on this plot. Okay, so here was the line we had before that looked like it kind of fit, but it actually was it gave us bad predictions on the endpoints. Here is our regression line. Okay, so now take a look. Let's go up to 72 inches again. So we have a 6 foot even father. Okay, and then we're going to predict his sons are around, looks like 6'1", so 71 inches. Okay, are we over predicting, under predicting, or right smack dab in the middle where we want to be? We're right about smack dab in the middle, right? So here's the people we're under predicting. Here's the people we're over predicting their heights. We're right in the middle. We've got the average. That's what we want the regression line to do, right? Is to predict on average what is the height of somebody with a father of that height. You go down here to 62 inches. So they're like 5'2". We're going to predict their sons are going to be like 65 inches. And we're wrong on the low end for this guy. For these guys, we're wrong on the high end for these guys, but we're going right about through the middle. That's what we want, our regression line to predict the average, right? For what we can predict. Okay, so our regression line seems to be doing what it is, and it says, okay, how many fathers, and this is some more historical things, how many fathers are 72 inches or taller? Okay, father 72, we can count them. That seems pretty cumbersome. What's a better way to find out how many fathers are 72 inches or taller? Let's use R. We say FS $ father greater than 72. Is that what we're asking? Yeah, 72 inches or taller. What do we get? We're going to get 1,078 trues and falses. We don't want 1,078 trues and falses. We want a number. How do we get that number? I heard it. Yeah, just sum it, right? Sum it, and that will coerce all of the trues to ones, all of the falses to zeros. It'll add up all of the ones, and we get there are 67 fathers that are taller than 72 inches. Okay, now how many sons? Same thing. Sum of FS $ son greater than 72. Okay, I'm going to execute both so we can see those. Okay, so we had 67 fathers that were taller than 6 feet. We had 118 sons that are taller than 6 feet. But our regression line says that somebody who is 6 feet is likely to have a son who is shorter than 6 feet. Okay, this is the historical stuff that we need to reconcile as they go, wait, the reason this is called the regression line is because they noticed this slope, which is this red slope line, which seems like the good slope, you know, the good prediction, turns out not to be a good prediction. Our better predictions are regressing. Shorter fathers predict taller sons. Taller fathers predict shorter sons, right? It regresses to the mean. That's what regression means, coming from the extremes towards the mean. That's a regression. So that's why it's called a regression line. Okay, so tall fathers who are 6'2", are predicted to have sons who are shorter than they are. But there are fewer sons who are 6'2" or taller. How do we reconcile this seeming paradox? We actually have more sons who are taller than 6'2", not fewer. But our prediction is that we're going to have taller fathers should have shorter sons. How is this possible? It's not that easy, so I'm not going to make you answer because it's this was a conundrum that the early statisticians doing regression were trying to figure out. And here's the reason. The average might be down, but that doesn't mean the extremes are, right? If you take a look at who are the sons who are 72 inches or taller, how tall are their dads? The shortest dad is 63 inches tall. There's a 63-inch dad. A guy who was 5'3" had a 6'3" son. or 6'2", looks like 74 inches. So 6'2", right? And that is because, look, this line is not perfectly predictive. There's a lot of variation around this line. And this formula for slope, I think, is very telling. That red line is the standard deviation of y over the standard deviation of x. It gives us bad predictions. How much do we regress the line or make it flatter? We regress it by the amount of how well it predicts, right? The correlation was only 0.5. So fathers are not deterministic. They do not determine the heights of their sons by themselves, right? Otherwise, we would see a perfect black line right along. All the dots would line up right on this red line. But they don't line up on that red line because a lot of other factors determine your son's height, like the mother's height, environmental factors, protein intake, and just random noise of your genes, right? If we added mother's heights to this regression line, we wouldn't get perfect predictions. There's just a lot of random noise here. But how much does that line regress? Depends on how much prediction you have in the system. This is not a perfect prediction, so we have to regress the line quite a bit. Okay, here's an analogy I'm going to say, is you say, all right, well, Michael Jordan, right? He was the basketball star I grew up with. We all idolized Michael Jordan when I was a kid, right? But arguably the best basketball player of all time. How good were his sons? That's a, illustration of regression to the mean. How good were his sons? They were decent. They were better than me, better than an average basketball player, but they did not ever go to the NBA. Maybe they played in college a little, I don't know, but they weren't that good, right? Regression, right? You have this extreme player. His sons are not going to be as good as him, right? Regression to the mean. And so, that's the same thing of saying, if you have tall fathers, but the average goes down, how do we get basketball stars? If Michael Jordan's sons aren't as good as he is, how do we get LeBron James? Well, the quality of the basketball player of the father is not a perfect predictor of how good they are going to be a son. LeBron James came from somebody who wasn't a basketball player. That can happen. There's a lot of variation in the system. Right. And so the amount of regression, that's our average prediction. How much does our average prediction go down? Depends on how well our system predicts. This system is predictive, but not perfectly predictive. There's lots of variation around this. So we have more regression coming down, despite the fact that sons' heights are not becoming less variant. They're not becoming shorter over time. It's a reflection of how much error is in the prediction model. Okay, so even though overall the regression to the mean, we get this regression of tall fathers don't produce sons who are on average as tall as them, we still have plenty tall sons because there's a lot of variation in the system, and even short fathers can have tall sons way over here, and LeBron James can come from somebody who wasn't a star basketball player. Okay, all right. Now, actually, what we're going to do is let's do the regression model, and we're going to save it as HTReg. Okay, so we're saying HTReg gets, and how do we do a regression model? With the command? LM for linear model. LM, and then we do this weird tilde thing. So we're going to predict son based on the father. So we do son is predicted by father, and we use this little tilde symbol to say this is our regression model. Dependent variable, tilde, independent variable. This week, we're doing the one independent variable. Next week, we'll have lots of independent variables, and we'll just separate them by plus signs. So we'll say father plus mother plus genes plus whatever. Okay, so that's our one input. This is the regression equation we want to predict. And then we say their data. Data equals FS. Okay, nothing gets outputted. It gets saved into HTReg. Remember our second week of the class, we talked about lists. We have not done anything with lists since then. Almost everything we've done has been data frames. The output of a regression model is saved in a list. Okay, so that's because there's lots of different pieces of content with different dimensions and different types, which means we can't put it all in a data frame. So we have to put it in a list, and it groups together a bunch of different things. Okay, but when we want to see the actual regression output, we just use our handy summary function. So we say summary of HTReg. So almost always, and maybe in this class always, you do your regression model, and immediately after that you say summary of wherever you save that. So summary of HTReg. Okay, now this is the part, nobody should leave this class without knowing this output and being able to interpret the important parts of it backwards and forwards. Okay, the important parts are this is your regression equation. it is 33.8928 plus 0.51401 times father, right? So son equals 33.8928 plus 4.514 times this father's height, right? Which is what we did already, right? We plugged that in. So we already found when we did our AB line here, it was 33.89 and then 0.514. Right. So that's the same thing. So it did this, the math works the same. Okay. So that's the thing, is you need to be able to look at these coefficients, construct the regression line. And this could have, it's always going to start with the intercept, then have your independent variable. Next week we'll have multiple independent variables, but it's just going to list them one after the other. And you just multiply this coefficient times the variable, right? No matter how many variables you have, always works the same. So trust on that and yeah, be very capable on that. Other thing you need to know is these p-values. Ignore the p-value of the intercept test. That doesn't matter. We don't care if the intercept is above or below 0, but we do care about our slope test. Okay, this slope, remember every statistical test, and the reason we did statistical tests last week is because I want you to be familiar with how a statistical test works. And regression has statistical tests. Every slope coefficient has a statistical test associated with it. This p-value is what? Less than 0.00 with 2 zeros too, right? So super, 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 super small, right? What was the null hypothesis on this? Remember, the null hypothesis is always some equality statement, right? So the null hypothesis is that the coefficient on father equals what?
Same as the sun.
What?
The same as the sun.
No, because the coefficient is a slope, right? So we're saying the coefficient, the same with the sun would be like coefficient should be 1, right? It's not saying 1. It's not testing whether the slope coefficient is 1 or not. It's testing whether the slope coefficient is what? Right? It's always equal to something. It's testing whether the slope coefficient equals 0, right? And the reason for it is this. I hope this intuition makes some sense to you. What if the dot of points looked just like this? No relationship whatsoever, right? Like father's height has nothing to do with son's heights, right? In that case, what's our best guess of a son's height? It would be the average of the son's heights. We would draw a flat line through it because the father's height has no predictive ability on son's height. Our best guess would just be a flat line, right? So if we drew a regression line when there's no relationship, the best regression line would just be a flat line, which would mean there's no point in drawing a flat line at all. That regression doesn't help us predict anything. There's no real relationship there, in which case so the null hypothesis is the slope 0. If the slope is 0, the regression line doesn't help us. And then your p-value is going to be above 0.05, doesn't really help you. Don't use this regression line. Okay, so this test is testing if we get a slope that's positive or negative, then that's saying, hey, there's a relationship we're finding here. So this test is this a real relationship, or is this a relationship just based on random noise? You happen to get some weird points that happen to draw the line slightly up or down, but it's not actually different from 0. Is this line different from 0? Yes, absolutely, right? Like the chances of us getting a slope this extreme, if it was just random points with no relationship, is 1 in what's 16 decimal places? 1 in, like, is that quintillion or something? Right? Like 1 in 1 quintillion. It's impossible. There is no way you get data this highly associated by random chance. So that's what that p-value is telling you. Okay, so each slope one is the slope 0, or meaning there's no real relationship there, or is, could this be attributable to random noise? Definitely not. There's no way this is just random noise. Okay, the other thing you need to know is this r squared, 0.2512. Okay, did I explain the phrase I want you to associate with r squared in this instruction, or is that next week? I think it was this instruction, right? R squared is the correlation squared. Okay, that's the one thing. We already calculated the correlation, right? The correlation was 0.514. 0.514 times 0.514 is 0.25, right? R squared. There's the reason it's called r squared, right? So it's the correlation squared. Why do we want the R squared? What does that tell us that the correlation doesn't? Why are we bothering to square it? The phrase I want you to remember is percent variance explained. Okay, and that is if I do a random draw of a sun and I say, hey, guess this guy's height. I don't know anything about this guy, right? I don't tell you the father's height. I don't tell you anything about him. I'm just gonna say, I'm gonna randomly grab a sun from this data set. I want you to guess how tall he is. What are you gonna guess? You have nothing to base your guess on. You have no information. What's your best guess? Yeah, the mean. You're gonna guess, what is it? What was the mean here? Way up here. You're gonna guess 68.68 inches. That's your best guess. You have no information to go on, right? But if I say, hey, I'm gonna take a sun from this data set, I want you to guess his height. But I'm telling you, his dad is 72 inches tall. Then what are you gonna guess his height to be? $33.8928 plus 0.514 times 72. Right? You're going to plug the father's height into this equation and get a prediction. Actually, let's go ahead and do that. So we say, hey, I'm telling you this guy's father is 72 inches tall. In that case, I'll say, okay, 33.8928. Oops, sorry. 33.8928 plus 0.51401 times 72. Okay, instead of guessing he's 68.68 inches, I'm guessing he's 70.9 inches. Okay, you're probably not going to be right on, right? Because it's a regression line. It's the average. That's your best guess knowing the father's height. But you're likely to be less far away than when you just guess 68.68 inches, right? Because now you have some information that helps you make a better prediction. Well, how much better is your prediction? 25%. R squared. Right? How far off are you likely to be? You're going to be 25% less far off using this regression line than if you just use the average guess. Right? If you say, hey, I'm going to draw 100 different suns from this data set, each one I want you to guess their height. If you have no information about the father's height, you're just going to guess 68.68 inches for every one of those guys. Right? But if for every one you use this regression line to guess their height, you're still going to be off on all of them. But your overall, how far off you are, is 25% less. So that's the percent variation explained. If you have all these suns with all these different heights, right? One sun is 62 inches, one sun is 74 inches, right? How much of that variation in height is due to their father's heights? 25% of it. So 25% of this variation in sun's height is explained by the father's height. Okay, so that's the phrase I want you to remember with R squared. Percent variance explained. Okay, so is the slope coefficient of 0.4514 due to random chance? That is this p-value here? Definitely not, right? The chances of it being due to random chance is 1 in 1 quintillion or 100 quintillion or whatever it is, okay? So definitely not. All right, now what we want to do is use this regression model to predict the heights of the sons of 5 different men. Sean Bradley, Shaquille O'Neal, Magic Johnson, Kareem Abdul-Jabbar, Boban Marjanovic. Okay, these are older NBA stars. Anybody know Sean Bradley? Does that name bandied around still in Mormon lore, right? So, yeah, so he was playing in the NBA when I was a kid. So, all right, so what we're going to do is create a matrix of dimension 5 by 1. I'm going to do this quickly so we can get through the whole predict exercise. So we're going to say, I'll call it NBAHT is going to be, we'll do a matrix. I put in my data points, which is 90, 85, 81, 86, 88. Okay, and then my other thing I have to do is n row equals 5. Okay, so we have, so NBAHT, let's just take a look. We have these 5 data points here. I want to actually plug those 5 points into my regression model to give me predictions of their kids' heights, right? At least their son's height, since this is a father-son prediction. Okay, but in order to do that, it needs to be a data frame and it has to have the exact same variable name. So I'm going to say NBAHT is going to be as.data.frame. Okay, or actually I can just use data.frame, not as.data. I can, either one will work. So I want NBAHT. Okay, so now NBAHT is a data frame. So if we take a look at NBAHT, now it's a data frame, but the variable name in there is NBAHT. I don't want that. In order for it to use this data frame to make a prediction, it has to be father. So I say names of NBAHT is father. Oops, I put a space in the wrong place. Okay, so now if we take a look at NBAHT, now it's a data frame. It is named father, the same variable as the variable in our regression model. Now we can just plug this data frame into our predict function in order to predict the heights of these NBA stars' suns. So I'm going to say, I'll just say predict. And the predict function needs, well, it needs one or two things depending on what you're doing. It needs one thing, and that is the actual regression model. Where is our regression model saved? Remember, this is our regression model, and we saved it into hreg. So in predict, we're going to say hreg. If I just executed this, which I can, it'll give me all of the predicted heights for all of the suns in the entire data frame. But that's not what we want. What we want to do is predict. I think it's new data equals NBAHT. And now it'll actually take this new data of 5 points, this data frame, and it'll plug that in. And we predict that Sean Bradley's sun should be about 80 inches tall. Shaquille O'Neal's sun should be 77 inches tall. Magic Johnson should be about 75 inches. And then Boban Marjanovic should be, his son should be 79 inches, right? Okay, the danger of doing this though. What is the problem with using our data set to predict the heights of NBA star suns? What was the tallest father in our data frame? 76 inches looks like. Right, how tall are these people that we're using? Are these NBA stars?
Much taller.
Yeah, much taller, which means we're predicting outside the scope of what we actually have data for. This is called extrapolation, right? And extrapolation is very dangerous, right? We don't know that the regression line is a line, right? We don't know that the relationship between fathers and sons' heights follows this nice linear pattern outside the data that we have. So that's something to always be careful of. I've done lots of projects before where it's easy to do, you know, like where you're predicting, like on advertising, you're predicting advertising response and the probability of response to an ad. Once you start doing extrapolation, suddenly you get like 70% probability of response. No ad gets 70% response rate, right? Like ad response is like 2 to 3%, right? And so that comes from extrapolation. You start, you know, applying this in the wrong area, and that's easy to do. Okay. What we want to do now is we're going to add the residuals and other results from the regression model to the original data. So we're going to use this augment function from the Broom package. And this is, do we do this on the instruction? Do you remember this? So we're going to call it fsaug. And I think we just use augment, and then we just plug in the actual regression model. Okay, so fsaug is 1,078 observations, same as in our data set, and it's got 8 variables. So let's just briefly take a look at that. So it has the son's height, father's height, just like in the original data. It has fitted. Anybody have any idea what fitted is? Our fitted value is our regression model. That's our regression model prediction, right? So our regression model, okay, taking the 65-inch father, we predict that their son will be 67.3 inches tall. The residual is what? What's the residual? The difference between the actual height and the fitted height, right? Or the predicted height, right? So the actual height of the sun was 59.8 inches. Our predicted value was 67.3. 0.8 minus 67.3 is a negative 7.5. Okay, so those are the residuals. The dot hat, dot sigma, dot Cook's distance, and standard deviation residual, those are other things we're not going to care about. Okay, all we care about is the fitted and the residual. Okay, next thing it asks us to do, and we're running out of time, but it says calculate the RMSE of the model. RMSE is the root mean squared error. It's a square root of the mean of the squared residuals. Okay, so only instead of taking the literal mean of the squared residuals, which would be the sum of the values divided by the number of values, we sum the values and divide by the degrees of freedom, which is the number of observations minus 2. Okay, so this is actually not that hard. It just made it sound really hard. So what we have to do is we have to take the mean of the squared residuals. So let's start with FSOG $sign residuals. What do I have to do with those residuals? I have to square them, right? The reason I have to square them is because the residuals, by definition, by mathematical necessity, add up to 0. Because you're in the middle of the line. Some of you're going to predict over predict. Some of the some predictions will be under predictions. So your residuals are going to be in equal parts, positive and negative. You add them all up, they add up to 0. Right? If we want to get a measure of how far off are our predictions, we square all the residuals, and then we take a mean of them. Okay, only the problem is the actual mean is like, we actually don't, a mean would be add them all up and then divide by the number you have. Because it's regression, we've used 2 degrees of freedom with the intercept and the slope. We actually have to add them all up and then divide by the degrees of freedom, which is the number of observations minus 2. So 1076 instead of 1078. Okay, and then, so actually we take that, 5.94, this is the average squared deviation, basically. So every guess is going to be off by 5.94, but that's squared. And so to get that a little bit more on the scale we're accustomed to, we're going to take the square root of that. Okay, so 2.438 is our root mean squared error. And basically it's kind of like an average. Okay, every father you give me, I'm going to predict his son's height. Okay, every prediction I give on that regression line is going to be off by about 2.44 inches. That's just the average amount I'm going to be off. That's my root mean squared error. That's on every guess on average is going to be off by about 2.5 inches. And that's about as good as we can do. Okay, the last thing it asks you to do is to calculate the R squared manually. And the R squared is basically how much is basically, you know, we know the R squared is 0.25, right? It's basically how much do our predictions get better using the regression line rather than just using the average. And I give you detailed instructions on how to do that. Do you want me to stick around and do that for you? Okay, you want me to take some extra time? All right, I'll go ahead and take the extra time here. We're just going to make this an extra long recording. Okay, we're going to calculate, so our most naive prediction of a sun's height, like I told you, if we had no relationship, we just guess the average, right? So we're going to say, if we were just to take the most naive prediction of every sun's height, we would just take the average of every person's height. So we'd say, so I'm going to say FSOG, this is our FS augmented data frame. I'm going to say, what am I calling it? The mean of the sun's height. I'm going to call this null res. Well, yeah. So our null residual is going to be the actual height minus the average, right? So that's going to be FS aug $sun minus the mean of FS aug $sun. Okay, so when I do that, I'm taking every sun and I'm going to say, hey, I don't know how tall you are, but I'm going to guess you're basically 68.68 inches, right? That's what the mean of FSOG is, right? $sun. We're just going to take every person's height, subtract the mean, and then we're going to save all of those in this column called null residuals. This is how far off are we if we just guess 68, the same average for every person. Right, so null res. I'm concerned that these null residuals, we have a lot of repeated values here. I don't know why that's happening. The sun's height are different. Why are they? Oh, they are. No, they're not the same. Okay. All right. So we've got the residuals. This is, remember, we've got our residuals here. This is how far off our prediction is from our regression line. Now we have these other residuals, which is, this is how far off we are just guessing average. Everybody's 68.68 inches, right? Which one should be farther off on average? The residuals from the regression line or the residuals from our null residuals from our average? Just guess, everybody's 68.68 inches. We should be farther off on the null residuals, right? Because that's an uninformed guess. Our guess should be farther off on average, right? Okay, now we're going to calculate the sum of squared residuals of null res, and that is, all we have to do is say fs aug $null res. We're going to square all those residuals, and then we're going to add them all up. This is our sum of squared residuals. So our null residuals, those are farther off. Those are not as good guesses. So when we square those and add them all up, 8,541.632. That's basically how much noise is in the data set to start with. We take all the sun's heights, subtract the mean, square all those, square them all, add them all up. It's 8,541. That's how much noise we started with in the entire data set. Okay, now it says calculate the total sum of squared residuals. Okay, that was the sum of squared of our null residuals. This is the residuals from our regression model, which should be better. They shouldn't be as big because we have a better guess now. So if we take a sum of fs aug $.resid, square those, add them up, it goes down to 6,396. We don't have as much noise anymore because we make better predictions. Well, how much did that increase? Or how much did we improve? We have our calculation of r squared. I give you the formula right here. It's going to be 1 minus sum of squared SSEM. That's the sum of squared errors of our model. And that is 6396.281 divided by the amount of error we started with, which was 8541.632. And we end up with 0.2511. Okay, does that number look familiar? That is our r squared from our model right here, right? 0.2511, although they rounded up to 12 because they had to round that last number. Okay, you will never have to manually calculate r squared again. But I wanted you to have that intuition, right? If we have a bunch of data, a bunch of noisy data, a bunch of sun's heights, they vary in height, right? How far off are we if we just guess the average? We're off by 8,500. Well, if we use the regression line, how far off are we? Not as far off because we have a regression line that helps us make better predictions. How much did our predictions improve? By 25%. Because the average squared deviation went down by 25% relative to just guessing the mean for every sun. Okay, I hope that helps. I think basically I did your entire homework assignment for you. So good luck on the homework assignment. I don't think you'll need it.